Hey Trick Class, we're going to look at our section notes on polar equations and graphs. So just a reminder, this is how we think of plotting points in the rectangular coordinate system. We go over to the right 1 unit, we go up 2 units from there. We go to the left, we go up. In the polar system, we have distance that's defined along the x-axis, standard position, and then we rotate as needed to get to the point we want. So again, here's the 2 on that circle of radius 2, and we rotate pi/4 radians, and we get that point. If we get on the 4 circle and rotate all the way around until we're in quadrant 3 over here at pi/4 radians, then that's the point for pi/4. Alright, another thing to remember with this, we talked about it in the previous notes, that if I rotate to, let's say hypothetically, I'm on the 3 circle, and I rotate to 3 pi/4, but I have a negative instead of a positive, then I'll actually go out the other side and land on that 3 circle. So that would be negative 3 pi/4. So the angle that we're given is a positive angle, and we rotate to that position, but because the r is negative, we come back the other direction. So remember, negative r's, we go back in the other direction. That's going to be important for this set of notes as well. So when we define a polar equation, it's just an equation where the x-coordinate, typically like what we're used to, the x-coordinates tell us how to get a y value. So I have here just a typical y equals f of x, a function where the x-coordinates get plugged in, and once we come up with what happens to that x-coordinate, we pick a number, so I'm picking 2. I'm plugging 2 into this equation. 2 cubed is 8, 2 squared is 4. Negative 3 times 4 is negative 12. 8 minus 12 is negative 4. Plus 4 would be 0. So negative 2 times 2 is negative 4. So this outputs negative 4. And so you pick a number, you plug in, and then we get a vertical change off of that number on the x-axis. So negative 4, positive 2 goes to negative 4 in this function. So that goes in. What comes out is vertically above it or below it. And that's the case for all these points, right? The x-coordinate goes in, we do whatever the function says to the x-coordinate, and we get a y-coordinate. And so it's kind of like the way I think of it is the x-coordinates are defined on the x-axis, and the function defines what happens to those numbers on the x-axis, and it kind of has this bending, twisting up of the x-axis. So that is the idea of a rectangular equation. Inputs are x's, and they get stretched up and down on the in the y direction. So in a rectangular equation, we find the y coordinate by doing something to x. We basically isolate y typically. Y equals mx plus b. Y equals x squared. We get the y coordinate isolated. And what that's saying is you pick something left or right. This will tell you how far up and down you have to go. That's what we saw in the previous visual. But with a polar equation, we typically isolate r. R is like the distance from the origin we are. And that makes r a function of theta. So we define an angle, a rotation off of that positive x-axis. And as we rotate, the distance from the origin changes based on that rotation. So right now I have r equals 2 cosine theta. So theta is my angle. So right now it's 0, and that means I'm on the x-axis. Well, the cosine of 0 is 1. 2 times 1 is 2. So the distance is 2 when I haven't rotated yet. But as I rotate, now the cosine of theta is now the cosine of 0.34. It's no longer 0. And cosine shrinks as we start to rotate. And so now we're not getting all the way to 2 anymore. So our distance is less than it was when we started off. And the more I rotate, the less that distance is. Until finally, when I get all the way to pi/2, remember, the cosine of pi/2 is 0. So when I get up to 90 degrees, the distance is 0, and there's nothing there. I've rotated to 90 degrees, but the radius distance from the origin has shrunk down to 0. So I've cut out this upper half of a circle. Now what we have to remember is as we come into the origin here, the angle is growing. And again, our radius is determined by the cosine of that angle. Don't forget that when we go into quadrant 2, when I'm getting ready to rotate this angle into quadrant 2, cosine becomes negative. and cosine is determining r. Remember what we said just a little bit ago. When r changes to a negative number, we go back in the opposite direction that we're pointing. So I added this little figure that I used in some of the previous videos to kind of help us with this. But when I am facing forward and r is positive, I move forward in the direction of the angle, defining the direction I'm facing. I move forward when r is positive. But as soon as we rotate beyond 90 degrees and cosine becomes negative, now r, notice r right here is this value. R is a negative number. And since r is negative, even though I'm facing into quadrant 2, I'm moving backwards behind me when I plot the point, because r is now a negative number. So these blue dots are just the same thing as, they're the same as these dots. They're just a collection of points that make this equation true. The y-coordinate is all this stuff happening to these x-coordinates. These dots are at these particular angles. At this one right here would be like at the pi over 6 angle, the radius is the square root of 3. When I get to pi over 3, cosine of pi over 3 is a half. I'm at 1. So these are just a collection of points in r and theta in polar that make the equation that we started off with here, r equals 2 cosine theta, true. All right, so when we dip into the negatives, we have negative values, r will be negative. Negative values for cosine, I should say. R will be negative. And so whatever direction we're facing, we actually move backwards to plot the point. All right, and as we rotate around, that stays the same. We still have negative values for r. And then when we get to the y-axis again, the cosine becomes positive again, and we start plotting points forward. So this actually cuts the same circle out twice in 0 to 2 pi radians. So we don't really need, like for this function, define anything beyond pi radians, because we cut out the complete circle in between 0 and pi. But just because we're used to 0 to 2 pi, I wanted you to see one full revolution of theta can cut out multiple plots of the graph. All right, but that's the big thing we've got to get used to, is a polar equation defines r, a distance from the origin, or distance from the pole, technically. The pole is not always the origin. The pole is just the point of rotation, where the rotation is defined from. It's just the distance of the pole is defined by the angle. All right, what would the equation r equals 4 look like? Well, r means distance, so the distance from the pole or the distance from the origin. Again, if the origin is the pole, the distance from the origin is 4. Well, that's a circle of radius 4. But how do we show that that's a circle of radius 4? Well, we can square both sides of this equation and get r squared is 16, and then we can use this thing that we saw from previous videos. It's just the relationship between x, y, and r. So a circle of radius r centered at the origin, if we drop a perpendicular from a point x, y that's on that circle, we get the Pythagorean relationship, x squared plus y squared equals r squared. So that r squared can then be replaced with x squared plus y squared. And there it is. There's the rectangular definition of a circle of radius 4. So r equals 4 is the polar version, x squared plus y squared equals 16 being the rectangular version. Much, because it's a circle, this is a circle, but we're defining a circle with rectangular coordinates. So it's much more complex than defining a circle with polar coordinates. Polar is basically 4 circular things. The grid itself is circular. So when we have a constant value, r equals a constant, that's just a circle in polar coordinates. All right, notice there's no theta here. So no matter where we rotate, it doesn't matter. The radius is always 4, and the angle of rotation does not affect that. All right, well, what if r is missing? What if we have theta equals a number? Well, you have to remember what theta is. It is an angle of rotation off the x-axis. So if there's the xy plane, there's x, there's y. If I rotate 3 pi over 4 radians, remember that will be in quadrant 2. So remember this is like pi over 4, 2 pi over 4, 3 pi over 4. So if I've rotated 3 pi over 4, now there's no r. So this is just kind of an infinitely long possibility of where we could land. If r is 1, maybe we're right there. If r is 2, we'd be right there. If r is 3, and so on. Well, what if r is a half? What if r is 1.5? What if r is 3/4? What if r is a quarter? 0.6? What if it's 0.1? You know, it's any collection of this. So what's going to happen is if I collect all the points I could get, I would get just this line. And because remember, r can be negative and we don't have r in this equation, we have to consider that we could actually end up going back the other way. And so what do we end up with? We just end up with a straight line. And because this is 3 pi over 4, these x coordinates and y coordinates are opposites. So this is technically the line y equals negative x if we plot it with rectangular coordinates. But again, how can I get that from just theta equals 3 pi over 4? How can I get to this? That's the idea. We're coming up with a rectangular equation. We need x's and y's and not r's and thetas. If we take tangent of both sides of the equations, we get tangent of theta equals, well, what's the tangent of 3 pi over 4? It's negative 1. And tangent is also defined as any point on the circle. It's the slope there. So it's the y coordinate divided by the x coordinate, and then multiply both sides by x, and you get y equals negative x. So that's how we can go from theta equals a constant to what that is defined to be. We can use tangent to get us there. Now technically we also use cotangent, but tangent's the one that will isolate y easiest because we just multiply by x here and we get y isolated. So there's what that looks like, again, showing that picture. Again, the theta equals 7 pi over 4 just goes with the fact that we could have negative r. So we'd be pointing it this way for theta equals 3 pi over 4, but because of the fact r could be positive or negative, we go back the other way as well. All right, what about if there's r's and thetas together? Well, that's where we're going to need all these different things that we've studied throughout the course. X is r cosine theta, y is r sine theta, x squared plus y squared is r squared, tangent theta equals y over x. There's all the different kinds of things that we could use to manipulate the equation that we have to get back to x's and y's. So for this one, r sine theta, I see that, I'm going to use that directly. Y equals r sine theta, so that left-hand side just becomes y equals 3. What's just interesting here is as I rotate, no matter how far I rotate, when I rotate, to pi over 4 radians, I'll hit a point on that line. When I rotate to pi over 2 radians, I'll hit a point on that line. Here I'll hit a point on that line. No matter where I rotate, I'll hit a point on the horizontal line, depending on what the value of theta is. So r gets stretched or compressed, depending on the value of the angle, to maintain that we always land on a horizontal line. All right, so when we want to use TI to do this, we have to switch into polar mode. Okay, so I'm going to show that on the TI. So when I press mode, one of the options that I have, there's radian degree that we've seen so far, but we also have FUNC function parametric polar. Right there's polar. And I can come down here and highlight and select POL for polar. And now when I press the y equals button, it doesn't have y's, it has r's. And these are the equations that I'm allowed to plot. So if I go back a couple and we see this equation r equals 4. If I just type 4 in here and hit graph, I'm going to hit zoom 6 to go back to a standard window. That is a circle, radius 4. I'm going to actually hit zoom square. So this will look polar. The circle will look circular. So there's a circle radius 4 by the equation r equals 4. Now, if I go to, this one doesn't have an r, so unfortunately I can't graph that in the TI calculator. But this one that had r sine theta equals 3, I could graph this as long as I isolate r. So I could do 3 divided by the sine. Now technically that's 3 cosecant, right? But I don't have a cosecant button, so on the TI I have to graph it that way, 3 divided by sine. So I'm going to type in 3 divided by sine, and notice this time when I hit the xt theta n button, it doesn't give me an x, it gives me a theta because I'm in polar coordinates. And when I hit graph, there's that horizontal line we were talking about. So the big thing, and it mentions it on this slide, is that you have to solve r in terms of theta. You have to isolate r. So on an equation like that, r equals 1 sine theta, I have to divide both sides by the sine function to get r isolated, which is going to be very similar to this one. It's just 1 sine theta instead of 3. So we're going to have a horizontal line at 1 instead of a horizontal line at 3. So this is the window that they suggest that you use for polar mode on this next window. So the way you do that is you just press window and you make your theta be 0 to 2 pi. So that's already 0 and 2 pi. If you don't recognize that as 2 pi, you can always just write 2 pi, and it'll give you the decimal approximation of that in there. Your theta step pi over 24. So I'm going to do pi divided by 24. Hit enter. There's that number. The x min is -8. X max is +8. X scale is 1. And then the y min and max is -5. Alright, and now we're ready to do the graph on the next window. So that's what this means. It's just in your window button on your calculator. And so now when I hit graph, it'll have that window, and we can see that it looks like theirs. It's just not blue. Ours is in that weird pea green color that these come in. Alright, if I did -2, r cosine equals -2, again, same thing. I need to divide both sides by the cosine, and this is the equation x equals -2. But I can't plot that. I have to actually type it. I can't type x equals on a calculator, just like I can't type theta equals. So I'll have to do y equals -2 and then divide by the cosine instead of the sine. Alright, same thing. I'm going to graph that. I'm sorry, I didn't divide. Second, insert, divide. There we go. Now, when I graph it, this will be a vertical line going through -2. Alright, so as long as the equation that you have has r's and thetas in it, and you can isolate the r, then you can get this into your calculator. So as we just saw, r sine theta equals a number is a horizontal line, r cosine theta equals a number is a vertical line. That's because r sine theta is y equals a number is a horizontal line, r cosine theta is x equals a number is a vertical line. Alright, well, what about this? This is slightly different. This is r equals 4 sine theta. So the r and the sine are separated. This is not the same thing. You can graph it on your TI, and when I hit graph, you can see this is not a horizontal line. This is a circle. So why is it a circle and not a horizontal line? Well, just what we want to try to do is get r sine theta, r cosine theta, r squared into these equations. We want to try to get this stuff: r sine theta, r cosine theta, r squared, tangent theta. We want to try to get these things to show up in the expression so we can replace them with stuff that's not in the boxes, the rectangular stuff. So in this equation, I have a sine and a theta, and I have an r, but they're not together, so it's not y. But remember, when things are equal, I can do the same thing to both sides. So what I'm going to end up doing here is multiply the left and right hand side by r, which will maintain the equality. It'll keep it equal, and I'll pick up an r squared, and I'll pick up an r sine theta. So we're going to multiply each side of the equation by r. We get r squared equals 4r sine theta. Well, r squared is x squared plus y squared. R sine theta is y, so this becomes x squared plus y squared equals 4y. And now we subtract the y's, so we get the y squared and the y together. So we're going to bring these together, and now this is a circle. Okay, it's a circle, but we need to complete the square to come up with the y center of the circle. This should be a y squared. So that's the equation of a circle whose center is 0 for x, 2 for y, and whose radius, remember this is r squared, whose radius is 4. Or sorry, the square root of 4, which is 2. So the center is 0, 2, the radius is 2. So there would be our plot, and it's exactly what the TI showed earlier when we looked at it. So there is a polar equation that's in a form that we kind of have to do some manipulation to get it to look like a rectangular equation that we're familiar enough with to be able to plot it. Alright, the same goes when we have a cosine instead of a sine. It's just that when we multiply both sides by the r, we're going to get an extra x coordinate instead of a y coordinate. So instead of the center of the circle moving off the origin in the y direction, the center of the circle is going to move off the origin in the x direction. Alright, we're still going to get x squared plus y squared, but now we're going to get 2x in there. So when we do our manipulation and regroup, complete the square, we end up with x minus 1 squared. So the center of the circle is at 1, 0, rather than 0 something else, because now we hit shifted in the x direction. Alright, Desmos can handle these, but unfortunately we're not allowed to use Desmos on the final exam, so I encourage you to practice with your TI. So if you look at these two examples, we have a when we have sine, r equals 4 sine theta, and we ended up with a circle that's centered up on the y-axis, and the farthest point up on the y-axis is 4. Right, this is 4. If you follow it up, that's 0, 4. And then when we did the same thing but with cosine, 2 cosine theta, if you look at that, we end up with a circle, and the farthest right point on that circle is 2. Right, that's always going to be the case. So when we have these values, again, we think of them as 2a. The center is at a, and so that makes the highest point of the graph at 2a. Right, same thing right here. The center is at negative a, but the farthest point below, like again, this is on the y-axis, so the farthest point down is negative 2a, the number that's in front of sine. And then the same thing happens for cosine. It's just left and right. The farthest point to the right is 2a. The center is at a. The farthest point to the right is negative 2a. The center is at negative a. All right, many times we're going to do tests for symmetry for these polar equations. So there's three main tests that we do, and they are for the polar axis symmetry, which again, that's typically the x-axis. The line theta equals pi over 2, which is typically y-axis symmetry. And then what we call origin symmetry or polar symmetry, symmetric to the pole. Typically the pole is the origin. And so when the pole is the origin, this is just x-axis symmetry, y-axis symmetry, and then what we refer to as polar symmetry or origin symmetry. The way that we do these tests is negate either theta or r, or sometimes both. This first test, they show all we have to do is negate theta. If you look really close, there's theta, and right down here is negative theta. So you replace theta with negative theta, see if you can get back to what you started with. That's the way that we do it. But we're just replacing theta with negative theta and seeing if that gets us back to what we began with. All right, when we check for y-axis symmetry, or again, they refer to it as the line theta equals pi over 2. If we replace theta with pi minus theta, and what that does is basically we're rotating this way, theta. Pi would be going all the way to here and then rotating back minus theta, going back the other direction. That's why it's y-axis symmetry. So we replace theta with pi minus theta and see, do we get back to what we started with? This will require the difference formula for sine and cosine often when we have sines and cosines tangents in our equations, because we're replacing the angle with pi minusing, or replacing something with a difference inside the sine and cosine tangent. So we will need the difference formula when we do that symmetry check. And then here for this one, we replace r theta with r pi plus theta, or an equivalent check would be just to negate r and see if we can get back to what we started with. So there's the three tests kind of written out in paragraphs, just basically what we just drew on there. All right, so when we graph an equation, again, just graph it in, take the time to graph it in your calculator. So there, I just typed what I see, hit graph, and there's the graph of it. So I can see that it looks like it has y-axis symmetry. Does not look like it has any others, but it will ask you to do those tests. So the symmetry checks, we replace theta with negative theta. The sine of negative theta is the opposite of the sine of theta, so we end up with instead of a 1 minus sign, we end up with a 1 plus sign inside of that bracket, and that's not what we started with. So when it's not what we started with, that doesn't mean it doesn't have that symmetry. That's kind of a weird thing to say, but these are checks for the symmetry. If we do get back to what we started with, it does have that symmetry. But if we don't get back to what we started with, it may or may not. It still may have the symmetry. So they're not going to be conclusive tests if they fail, if we don't get back to what we started with. All right, so here's the one when we replace theta with pi minus theta, we end up with the difference formula. So we got the difference formula for sine here. So we end up with sine pi cosine theta minus cosine pi sine theta. And when we do the math, the sine of pi is 0, so this whole entire term is going to go away. And then we end up with negative times a negative is a positive sign. But it's 1 minus that. So subtracting a positive sign is the same as subtracting sine. So we end up with what we started with. So because we're back to, again, there's what we started with, 2, 1 minus sign. And after we did all that math, we ended up with 2 times 1 minus sign. So we are back to what we started with. So we do have symmetry with respect to the line pi equals, or theta equals pi over 2, the y-axis. But we saw that with the graph. Okay, well, when we check for the pole symmetry, we just replace r with negative r. So multiplying both sides by -1, we get r equals -2 times the sine of 1 minus theta. And because of that, we don't see the test pass. Okay, it doesn't pass. That's the easy version of this test, but we're going to show that if we replace theta with theta plus pi, that we're going to fail that test too. So this time, when we replace theta here with theta plus pi, we'll need the sum formula for sine. So sine theta cosine theta plus cosine theta sine theta. So that's a -1. So that's a negative sine of theta. This is 0, and we're not back to 1 minus sine theta. We're at 1 plus sine theta in the bracket. So the test fails. So again, we may or may not have symmetry at the pole. It doesn't conclusively have it. But again, we saw with the graph, this does not have polar symmetry. Let me just show you real quick. Polar symmetry, let me blow this up so it's visible. If I had polar symmetry, if I picked a point that is for sure on the graph, and I went straight through the origin and hit another point. Sorry, straight through the origin, hit the origin, and then came out on that same line until I hit the graph again, and I hit the graph right there. If there was polar symmetry, then this distance right here would be equal to this distance right here. And you can see they're definitely not equal. So that's not going to have polar symmetry. If there were x-axis symmetry, the very first one when we replaced theta with negative theta, then this point would be like right there. It'd be the same distance above it as it is below, and obviously it's not. So there is no x-axis symmetry. But we do absolutely have y-axis symmetry. So if I folded this thing over at the y-axis, then this point would hit right there. This point would hit right there. And this point would hit right there. So this definitely has y-axis symmetry. It's just that we call y-axis the line theta equals pi over 2. So that's the only symmetry that we can see when we look at it. And that's the only one of these 3 tests that actually passed. All right, if you're plotting one of these by hand, you're literally plotting points. You're finding you just come up with different values for theta that are on the unit circle, and you are plugging those values in for theta and these sine, these trig functions that are on the right side of the r. So sine of negative pi over 2 is -1. Replace that, I get +4. Again, you're just evaluating. Unit circle would be essential here because you're evaluating the sine, the cosine, whatever happens to show up in these equations at these different values for theta to come up with points. So this is the distance at negative pi over 2. This is the distance at negative pi over 3. I'm plotting these distances at these angles. So there's what it would look like at negative pi over 2. We got 4. At negative pi over 6, we got 3. So that there's the 3 circle, there's the 4 circle. It'd be nice if these were all whole numbers, but again, occasionally they're not going to be when we're at certain values. So we just kind of have to estimate. There's the 3 circle, there's the 4 circle. So 3.74 is, that's 3/4 of the way roughly to the 4 circle from the 3 circle. We just have to be able to estimate distances if we're plotting these by hand. But again, luckily you won't have to estimate these very often. You can just graph them in your TI. All right, let's graph another equation. So there's 4 plus 2 cosine theta. I'm going to do graph. There's what I see. Okay, but again, they're going to ask in your homework to do these checks for symmetry. Does it have the check or not? Looking at that, it looks like it has x-axis symmetry. Definitely doesn't have polar symmetry. Definitely doesn't have y-axis symmetry. So the only test that I would expect to pass is the x-axis symmetry, which is when we replace theta with negative theta. So the cosine of negative theta is the same thing as the cosine of theta by the even property of cosine. So we do get back to what we start with. So it does have polar axis, again, which is x-axis symmetry. But when we do the other checks, like plugging in the difference formula for cosine, simplifying, cosine of pi is -1, sine of pi is 0, we end up with just 4 minus 2 cosine theta. And that's not what we started with. So it may or may not, but we saw that it does not have that symmetry. All right, when we replace r with negative r, obviously we're going to get negative r equals this. So dividing both sides by -1, we'll have -4 minus 2, that's obviously not the same. And then it also mentions here that if we replace theta by pi plus theta, use the sum formula for cosine, it also fails. It does not have that symmetry we saw at the beginning. So the next thing is to plot the points, and the same thing as before. Pick some key points and plug those numbers. Again, all of these are just numbers from the unit circle so we can evaluate them. And then when we plug those in, we can see that this graph, as we rotate, begins shrinking, gets smaller and smaller and smaller as we go all the way around the axis. And then it starts to grow again once we keep rotating beyond. The distance begins to start growing again until we get back to where we started with. So it has that funky looking shape there. All right, and then all of these are the same. So when you start off, you're just going to graph them in your TI, see what they look like. This one's got a funky little loop in the inside, but we do have, again, x-axis symmetry there we saw. We don't have any of the other symmetries. So when we plug these in, we're going to get something that's different than what we started with, and we don't have those symmetries. Again, just plotting the points, picking careful points on the unit circle that can help you evaluate. So this is, again, just showing you how important that unit circle is going to be when you're doing these types of problems in your homework or on like a final exam. And for this one, I want to just give you an example of one that is symmetric to all three, like all three tests for symmetries pass. But the thing is, like when I plug in negative theta into this, I can easily see that I'm going to get back to what I started with because it's cosine. So I'm back to what I started with. So we have that symmetry at the polar axis, the x-axis. This is a check for symmetry at the y-axis. So replacing theta with pi minus theta, using that property here, I'll distribute that through. This is -2 theta. -2 theta plus 2 pi, that is the period of cosine. So that means we end up at positive. It's the same thing as positive cosine 2 theta, because again, -2 theta is the same thing as 2 theta for cosine, that even property. So these are equivalent. That's when we're back to what we started with. So that means it has y-axis symmetry also. And because I have y-axis symmetry and x-axis symmetry, because I passed these two tests, I don't even need to do the third test. Because we have those first two symmetries, we automatically get polar symmetry. And what that means is, like, polar symmetry is, if I have a point, I go through the origin, I come out the other side, I'll be the same. Well, the first test said x-axis symmetry, so I know I'm going to have symmetry there. The second test said I have y-axis symmetry, so I know I'm going to be symmetric here. So therefore, I will have polar symmetry as well. So passing the first two tests automatically pass that polar test. All right, and then again, just plugging in the key points, seeing what you get. Graph this with your TI. These polar graphs are really interesting when we start to look at them like this. So there is 3 cosine 2 theta. You can press trace on these, just like trace gave you points that were on the original graph, like with rectangular coordinates. It does the same with polar. It just gives you x and y. It doesn't give you r. So there's rotating by 0.13 radians, 0.26 radians. All right. You can plug in different values you want, like specific values for theta. It'll tell you what the x and y coordinates are there. If that's something that would be useful to you, to help you. But notice it's just not giving you r. All right. It's giving you x and y. It's still giving rectangular coordinates even though we're in the polar mode. It is giving us the angle, but it's not giving us r. We would have to square this, take the square root to get r, unfortunately. So just know that it will, as you go through, it will kind of show you how it was formed as you move forward. So this was not, it wasn't this and then this and then this. It shows you the path through as we go from 0 to 2 pi. And it is it's important that you understand how they get formed as it is that you can see what they look like at times. So just understand the trace button still works here. It just doesn't give us r. All right, one last graph I want you to see is when r equals e, the exponential base. The second ln is e to a power. And now theta is being divided by 4. So x is theta divided by 4. And then when I graph this, I want you to see what happens. It just starts from the center and starts to go out from there. And this is what we refer to as a spiral. We stopped at 2 pi. But if I kept going, if I did 4 pi as my max instead of 2 pi and graph this, it's going to spiral and go around again, and just the spiral gets bigger and bigger and bigger as we make our way out. So this is a spiral because the radius is exponential. Exponential means it grows exponentially. If you recall, the exponential function starts off really small and then it takes off and gets larger and larger and larger. So this is what is actually happening here, is the radius is defined by the heights of this exponential curve. And as theta goes on, this is theta, moving left to right. And the r we're getting grows. It gets bigger and bigger and bigger as the angle goes. So the more we rotate, the more these angles are getting bigger, and they get larger and larger and larger and go off the screen as we continue to rotate. So that's why this graph has the look that it does. All right, you can test all these values. If I replace theta with negative theta, e to the negative power falls left to right. So it's not going to be the same as when it's growing left to right. So that's definitely not going to have x-axis symmetry. When you replace theta with pi minus theta, again, theta is negative, so again, it's going to be falling. And then when we replace r with negative r, this also is not going to have any of the symmetries. And it makes sense. It's not going to have any of the symmetries because as we rotate, we spiral and get larger and larger and larger. And that's not going to have x-axis symmetry, y-axis symmetry. It's not going to have origin symmetry. When I go through the origin, come out that same distance, when I get down here, I'm going to be rotating out further. So it's not going to have any of the symmetries that we define here. So it's going to fail all those symmetries when we have a spiral like this. So there's just a brief picture of it, but you can see the more we rotate, the further out we go.